to calculate the thermodynamic properties, PV and also temperature. Okay, so we actually how is depending on the pressure and also temperature if you want to calculate volumes, especially also for the temperature. Okay, so it's depending on the what equation that you can use, whether ideal gas, okay, virial equations. Okay, so virials um, is applicable for low to moderate if for two truncated, right? And then what else? And then for three truncated is applicable for the high temperatures. Even for high temperature is up to 50 bar. And for the moderate is around 1 to 15 bar or 20 bar. 10 bar is also considered as a moderate pressure. Okay. Um, and then we already explained also about the cubic equation of state. Okay, how to calculate by using Reddick-Kwong, soft Reddick-Kwong, Penn-Robinson, van der Waals, uh, also vapor-vapor and liquid-liquid equation equations. So we need the information from the cubic equation of state. Okay, wait. Okay, so and then we have another equation, which is generalized correlations. We call it as a pizza, Lee Kessler and also pizza videos. So it's depending on the pressure also. Okay, if just a model, you can use virial equations. Okay, and then we have what we call it as a special equation for liquid, right? So that one is by using the information of VC and also ZC. Okay, so for this one, okay, for this chapter, what we are going to focus is on the heat, okay, heat effects. So for heat effects, actually we divided into single phase and also uh, what is it? Uh, Sensible heat, latent heat, single phase, and also two phase. And we have a heat of reaction, heat of formation, and also heat conversions. I think some of this one, some of this heat, we is already covered in energy balance, I think. Okay, but for today's just recall back what you have learned in during your mass and energy balance class. Okay, so what we're going to cover is a sensible heat and heat capacity. What is a heat capacity? Okay, heat capacity is important for the calculations. This is showing about the if you compare between two materials, like which one can store the heat is much longer than the other materials. Okay, for example, like a wood and also aluminum, right? So which material is can store the heat is much longer? Okay, whether it's wood or aluminum. Okay, so that is the concept of the heat capacity. And then latent heat, standard operation, also heat of the industrial reaction. So since no reactions occur at the ambient temperature or ambient pressure, so uh, the reactions for the industrial processes sometimes is high pressure and also high temperature. So we need to determine how to calculate the especially the the change in enthalpy lah, before we calculate the heat. Okay, because no information we can get at 200 degrees C or 50 bar. So that is a very difficult, and it's a very limited information, okay, that we can get to calculate the enthalpy at, for example, at 50 degrees C or at 30 degrees C, right? Mostly we can get the information at the reference state, 25 degrees C and also 1 bar. Okay. So I will explain about the introduction of different type of heats, and especially the sensible and also latent heat. Okay, I think for the first one is uh, what is the sensible heat and what is the latent heat? Anyone know what is the difference between sensible heat and also latent heat? Hmm? Anyone know? When we should use sensible heat equation and when we have to use latent heat equation? Anyone know? What is the difference? Nur Umaira, do you know? Nur Umaira, are you there? Nur Umaira, Nur Umaira, ada tak? Nur Umaira? Yes. What's the difference? Nur Umaira, ada jawapan tak? What's the difference? When you should use the sensible heat equation? Not sure. You guess? Any answer? Umaira, Umaira. Anyone? Several cause change in temperature about latent heat. Yes. Okay. So, if there is a change in the temperature but no change in the phase, so you have to use sensible heat. Okay, sensible heat equation. Okay, but if there is a change in the what is it, phase, but no change in the temperature, so you have to use latent heat, meaning that there is a, for the latent heat is for two phase system. Okay, so you have to understand. For example, like a water, right? Okay, like a water, hijau, tak apa lah. Right. So, okay. So this is a change in, for example, this one is a 0 degree lah. 0 degree, different negative 20. Right. Then 20 plus this one 100. So here is ice and water. This one is water and vapor or steam. So this one you have to use latent heat. This one is sensible heat. Okay? Because this one change in temperature. This one change in phase, but no change in temperature. So you have to remember that. Okay. But if during duration there is a change in temperature and change in the phase, you have to combine these two heat. And there is a reaction, you have to add another heat, another enthalpy, the calculation of change in enthalpy for the heat of reaction, so that you can get the total heat. Okay, Stan? Faham eh? Okay. So let's see for the pure substance. Okay. Yeah, I think all of you know that chemical process involve the heat transfer. What else? A reactor, right? A distillation column, separators, right? So involve the heat transfer lah. Okay, in the pipeline also there's a heating and cooling. Okay. So for example, if you want to design the reactor, you have to know the knowledge of the heat transfer lah. Especially if you want to know if you need the knowledge of heat transfer, it should be the association between the thermodynamic and also chemical reaction. Okay, heat effects of course we call it as a thermodynamics Okay, so all these things we the information about the knowledge about thermodynamics is important to evaluate the what is it, the heat effects where the heat of combustion, heat of reactions, right? Okay, what else? Heat of formation. Heat formation is important for the calculation of heat of reaction. Okay. Okay, so you have to remember these 5 heat effects. Okay, sensible heat, latent heat, heat of reaction, heat of formation, and heat of combustion. Okay, so these 5. Okay, we go see on the sensible heat effects. Okay, for examples, for the sensible heat, okay, if you look at here that heat transfer to the system. Okay, when you apply heat, cause the T of the system change. Okay, no phase, no reaction, no change in composition. This one you have to know. This is the key. Okay, because later you will do the hypothetical part. Maybe there's a change in temperature, but and then change in the phase, right? And then there is a heat of reactions, right? And then change in the phase, change in the temperature, and then you can get delta H. Okay, there is a latent heat, sensible heat, heat of reaction, right? This is under the reference state Okay, we have to bring it to the reference state 25 1 bar because we have information at the reference state. That's why we use. Okay, and then you can calculate the total change in enthalpy, and from the change in enthalpy times with the number of mole, so you can get heat transfer. Okay. Okay. So first, if we consider the pure substance, a closed system, constant pressure, right? Initial condition is T1 and P1, and final condition is T2. Okay, but pressure is constant. Okay, the change in temperature, no reaction, no phase change. We look at here that liquid is going to be the volume is going to be almost similar, but the gas, the important thing is the gas. See this one is going to be increase the volume. Okay. So for the closed system, if you look at there is a dq plus dw. That one is a energy balance. Okay, du plus dek and dep. Change in the what is it, potential and kinetic energy. That one generally is very small, so we can neglect that one, right? Okay, so it's become dq minus pdv equal to dq. Okay, so this is the relationship of how to calculate the enthalpy. Okay, H equal to U plus PV, as you know, right, from the mass energy balance, and U equal to DH minus PdV, right? Okay, so this is how to calculate the Q is equal to delta H, but the problem is how can we calculate that the change in enthalpy? Okay, this is what we have to find. So if what we call it as what is it, ideal gas, right? So we just from the MCP dt, so dt is just a delta T2 minus T1, okay? But how about is a very high pressure, right? Wide range of the temperature and also pressure. How can we calculate that one? Okay, we need the integration, and also we have a special equation. It's very long. Okay, so you have to know that the equations. Okay, for the specific enthalpy, delta H, if you look at here that summation of a T, right? This one integration of T2 to T1 CPDT, but valid for isobaric process and no change in the phase. True for ideal gas. This is for ideal gas, only for ideal gas. How about non-ideals? Now we are focusing for the non-ideal system. Okay, you have to remember this is only true for the ideal gas or very low pressure. Okay, as I mentioned in the previous class, right? Considering the pressure, if we want to consider as a ideal gas, okay, it should be between range of 0.98 to 1.02. Okay, we still remember that graph. All right. So for the real system, I don't think there is a there is a we can apply. I don't think we can apply for the real system. Okay, but this one is for the internal. What is it? Internal energy. Almost similar. Only this one is we change in term of CV and also delta U. Okay. Okay. Is it clear? Also for ideal gas and incompressible liquid. Okay, so let's see this one. The example I think is based on the ideal gas. Okay, we can solve it actually if we want to calculate TA2, right? Is hot oil T01 and this one is A1 TA1 and out is exit is TA2. Okay, when T02, what is the TA2, right? Okay, this one TA2. Okay, what is how to calculate this one? But if we consider as an ideal gas, we can solve for TA1 actually. Okay, if we considering the ideal gas, okay, we can solve. But considering if high temperature, okay, uh, uh, we cannot solve it as simple as like this. Okay, just change in temperature delta T2 minus delta T1, right? This one. Okay, we need a special equation. Okay, we need special equation. I don't think we can solve it like this one. Okay. Okay, heat capacity. What is the definition? As I told you, of course, idea of the heat capacity is if we compare right between the penny and also marble, as I told you, right? Okay, so which one is stay hot longer after being removed from the heat source, right? Okay, once you remove this one, which one is the longer? So that is the concept of the heat capacity. Okay, the highest specific heat capacity stay is gonna be longer lah. Is a what is it? Have a longer is a how to say? Sometimes it's become if we compare like if marble and penny, which one? It's gonna be shorter, right? Marble. Penny is much longer, but aluminium foil is still longer. Okay, that one. Okay, okay. So alamak, why cannot move? Okay, what happened? Ah, sudah. Wait asal tak boleh bergerak pula ni. I cannot see the. Ya, tak boleh jalan. Wait kenapa ni? Cannot go to the next page. Aduh. Let me share the point. Okay. Jangan pakai sini pula. Where's the heat capacity? Okay. Okay, this one. Okay, so I hope that you know how to what is the concept of the heat capacity. Yeah. So um okay. So for the heat capacity, this is important for the calculation of the for the real gas system. Okay. If you look at here that to determine the you need the how to say parameter a constant heat capacity, right? A, B, C, and also D. So where we can you can get this A, B, C, and also D, please refer to the table. This is appendix C, I think. Okay. Please refer to Appendix C. Okay. If not Appendix C, maybe Appendix D lah. Okay. For the old book is Appendix C. I think for the new book is Appendix D. But this is a stated the title for the Appendix C is the heat capacity for the gases in the ideal gas state. Eh? There is also for the solid and also liquid. Okay. So please refer to this uh, tables. Okay. So for the ideal gas, just using CPIG, ABT, A, B, C, and also D. Okay, but if relationship between heat capacity, sekejap. Okay, so if you look at this one, okay, the example, given the molar heat capacity CH4 in the ideal gas state, it's already state is a ideal gas. Okay, what you have to do, just substitute the temperature, so you can you can calculate CP. Okay, and from this one you can calculate the change in enthalpy. Okay, so this is very short example. Okay, for the evaluation of the sensible heat integration, this one if the temperature is high, okay, for example at 200 degrees C, okay, and then for example you want to determine the heat capacity, no, you want to determine the enthalpy as well, and then after that you want to determine the heat lah. Okay, a change in enthalpy, and then you have to determine the heat lah. Okay, is given the initial temperature and final temperature. There's a two cases here. You can use this equation. Okay, you have to remember this one is for the heat integral, which is we consider for the real system. We don't use this one anymore. Okay, this equation. We don't use this one anymore. This one. We didn't use this equation anymore for the calculation. Okay, so we have to use this equation. Please highlight in the PowerPoint as well as in your textbooks. Okay, so you need to use this equation. So there's a two cases, which is case 1 and case 2. For the case 1, okay, is given a T naught and also T. This one. So you want to calculate the heat transfer. Okay, delta Q. This is a straight calculation. It's given T naught and T1. You just substitute, determine the tau. Tau is T divided by T naught. T naught generally is the initial. It's not given is a standard state 25 degrees C, 1 bar. But generally, if T naught is the entering the reactor, okay, entering the reactor, and the final is going to be exit of the reactor. Okay. So case 2, we want to determine final temperature. This one. Okay, case 2, we want to find the final temperature. It is given T naught, Q or H, but we have to do the what we have to determine the temperature. What we have to do is we have to do the iteration process. Okay, by factoring T tau minus 1. Okay, factoring. Okay, just factor this one. You put it outside. Okay, and then we make it we make it into mean heat capacity. This one. This one in terms of mean heat capacity. Okay, so you have to highlight this one. So meaning that this is the equation. Okay, and your equation, once you rearrange this equation, your equation will be in expressed in terms of T equal to delta H divided by C P H plus T naught. This one mean heat capacity. So what you have to do, okay, you have to guess the initial, because it's given the initial temperature. Okay, so for first guess for the temperature, which is the finals, it should be more than T naught. Okay, so that one you have to remember. Okay, you have to guess more than T naught, and then substitute into mean heat capacity, this one, right? Okay, so once you substitute here, right, this one should be times with R to get only CP. CP you substitute here. Okay, and then you calculate T, and then you get new T. This new T you substitute again to the CP. Substitute lah here. Okay, and then until it convert, you can get final temperature. Okay, There's these two cases. Okay. So this is the examples one, example three lah for the case one. Okay, if you look at here, that is given the initial temperature and final temperature. Okay, one more. So what you have to do is just calculate, directly calculate by using this equation. This one. Yeah. So you can get an answer lah. Okay. So if you look at here that Q delta H, right? R this one and plus this one. This is the longer equation just now. Okay. So you need times with R for to get the Q. Okay, because this is one more, right? So actually is N this here. And one more. N times with delta H. Okay. Okay, so you can get Q. However, for the case 2, if you look at here that um, is given the number of mole, degree, the temperature and also pressure, but we have to find the final temperature. Okay, how to calculate? Please determine the delta H first, because delta H equal to, okay, Cp dt. This one. Okay, so this is for the case 2. Okay, what we have to do, we rearrange in terms of what is it, Cp dt. Okay, MCPH, this one is actually for the mathematical calculation if you use the software. Okay, actually it's mean heat capacity lah. MCP mean heat capacity. Okay, for the enthalpy. So this one is initial temperature. This one. This one is our target temperature, the final. This one is the value of A, B, C as well as D. How to find this A, B, C, and D? Okay. Please refer to table C lah. Okay, heat capacity and also property change for the of the formation. Okay, so to determine the value of this one A, this one B, this one is C, this one is D. Okay, plus, minus. Okay, okay. Iterations, we have to start with T more than T naught, since if you look at here, that temperature is around 533. Okay, so you can start with the maybe 600 Kelvin or 1000 Kelvin. It's up to you. Okay, it's up to you. Okay, and then you do the iterations. Okay, do the iteration just like this one. Okay, this one, just like this one. Okay, this one, this one, this one. Just substitute into this equation. Okay, let's redo this tutorial. Please take one paper. Okay, and we do this together. Tutorial 1, okay? I want you do this one for A. For A. Okay, for steady flow in the heat exchanger, approximate atmosphere okay, approximately atmospheric pressure. What is the heat transfer? Okay, So if you look at here, first you have to identify what is the initial temperature and what is the initial pressure. Okay, T naught. Okay, T. And what else? Number of mole. Please convert into Kelvin. Okay. This one 200 degrees C. Okay, this one 1100 degrees C. Number of mole 10 mole. So for SO2, please refer to table C1. A, B, C, and also D. This is the constant. Please give me the constant now, the value. Okay. A, B, C, and D. Okay. And then this one you can calculate tau lah. So what is the tau? T divided by T naught. Okay. From the equation, okay, delta H equal to T2 T1 Cp dt is equal to, right, R dot I. This one I'm using ICPH integration. CPH T naught T A B C D. Okay, A B C D. So please calculate by using delta H equation. Okay, R times with A T naught tau minus 1 plus B divided by 2. Okay, T naught power of 2. Okay, tau power of 2 minus 1 plus C apa equation ni? C divided by 3. Please do, okay? I will randomly pick one. This one 3 minus 1 plus D divided by T naught tau minus 1 divided by tau. And close. Okay. So please calculate delta H. Don't remember, please, since we want to determine delta H, so should be times R. This one. Okay. R constant. Okay. So since if you look at it, once you substitute all the values A, B, C, and D, and also tau inside these equations, cut Q equal to N delta H. So you can get Q lah. So we have a 10 mole times with 10 mole. Please calculate. Do not forget the unit. So give me the answer. Apa eh? Wopohi. Poyi, poyi.
After I'm calculating.
Okay.
Sir,
Yeah.
just now
What's
yeah, at the C for the question for the chemical sulfur dioxide lah. The C
SO2?
is the only dot don't have the data. What does dot mean ah?
Dot. Awak kena tengok sampai ke belakang. Tak ada lah. That is a zero equal to zero.
Oh, zero. Okay,
But
okay.
no value is equal to zero.
Oh, right. Think of it.
Yeah. What's the answer? 11693 kilojoule per mole. Is it correct? How about anyone? Why kilojoule per mole? Delta H. You have to calculate the Q. Should be normal. Because its total is 10 mole. So times with the 10 mole. What's the answer? 470. Okay, that is the answer. 470. Please not send privately. Okay, just share with your friends. Saya bukannya nak jawapan ni. Okay. Everyone should know the answer. Saya tak perlukan jawapan. Okay. So the answer is 470.0 470 lah kilojam. Okay. That's the answer. Okay. Similarly also you can do for B lah. Okay, for B. Okay. Can you do for tutorial 2? Give me the answer for tutorial 2. If you look at here, how much heat is required when 10,000 kilogram of CaCO3 is heated at atmospheric pressure from 50 degrees C to 880 degrees C? This one. So it's the same. Okay, only what you have to do is initially you have to convert this one to mole. Okay, number of mole. So because it's 10,000, right? 10,000 kilogram. So just divide it by the molecular weight so you can get N. Okay, and the rest is going to be the same. Okay, the same step as you do for A. Okay, so I don't think I need to give you how to say show you the step for the calculation because it's the same. Okay, what you have to do is just identify initial temperature and initial pressure, right? And convert it into Kelvin, and then determine tau. Okay, T naught and then T, right, and then tau. What else? Determine A, B, C as well as D, and then delta H equal to summation of Cp dt. Okay, then this one is you have to make it enlarge R delta H long equation. Okay. Okay. So just as delta H, then Q times with N delta H. So you can get the answer. Okay. So it's just a direct calculation. Okay, any questions about the about the sensible heat? Any questions before we move to the latent heat? So you have to remember, okay, two cases. If it's given T naught and also T, so what we have to do, we have to calculate Q, okay, and then if T is not given, which is the final temperature, and it is given the Q, so you have to calculate final temperature. So the problems, the tedious part is how to do the iteration. Okay. Any questions? So I guess no questions. So let's we move to the latent heat of pure substance.
Betul.
Okay. Yes.
Untuk kira tahu kena guna dalam Kelvin.
Atau no value. Tapi it should be in Kelvin lah. T divided by T naught.
Okay, thank you.
Should be in Kelvin. Okay. Okay. So for the latent heat pure substance, okay, if you look at here that latent heat for the pure substance, this one is for the two-phase system, two phases. Okay. So you have to remember, just now sensible heat, right? Sensible heat, we done it, and now is we look at the latent heat. Okay, sensible heat by using heat capacity, but latent heat they have their own equation. Okay, this is for the two-phase system. Okay, for the latent heat, pure substance at constant pressure and no temperature changes. Okay, so it should be constant. Okay, from the solid to liquid is going to be liquefied, and liquid to the vapor is going to be vaporized. So between solid to liquid, we call it as a fusion, and then from the liquid to the vapor is a vaporization. Okay, so there is a heat transfer in this two-phase system. Okay, so we call it as a latent heat. Okay, so this is the example. If you look at here, that latent heat is within this for the ice and water, right? This one, because of course you at the 0 degrees C, right? When even if you let it the ice, okay, at the room temperature, right? I think it's the room temperature or room temperature. Oh yeah, so it's gonna be melting, right? So there's a two-phase system. Similarly, also at 100 degrees C. Okay, I think this one is at 0 degrees C. Okay, for this one, for two-phase. Okay, this one. Okay, and this one at 100 lah. If you boil the water, right, there's a you can see the bubble and also the liquid, right? And that when you boil the water, so that is what we call it a two-phase system. Okay, but if there's a change in temperature but no phase change, for example, you want to heat the water from 30 degrees C, right, to 100, right? So the temperature when you boil is it keep increasing, but the phase is still same, is a liquid. Okay, until it reach the boiling point. Okay, information of the process. If you look at here, that pure substance initial conditions. Okay, this is the just information that for the process of to get the latent heat. Saturated liquid. Okay, we call it if you still remember, right, for the PV diagram, right, two-phase system is this one. This is a liquid, right? Solid. Okay, so it lies between this area. PV diagram. Okay, PV diagram. Okay, but if PT diagrams, diagram ni. Asal tak ada ni. Biru juga. Tak ada tukar. Okay. PT diagram. This one. This one. This one is critical, right? This one. On the line, this one. Okay. 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 So saturated liquid is first bubble appear, meaning that mostly is almost 100% is liquid. Okay, we can consider as 99%. Okay, and final condition, saturated vapor, last drop disappear. Okay, almost all the liquid is become vapor. Only the last drop we call it as saturated vapor. Okay, there is a phase change and no, you have to remember that. Well, later in chapter 10 we will do calculation on the bulk point and dew point. Okay, what is the equation? Okay, that is important lah. First bubble and also last drop of liquid. Okay, you have to remember these four equations. Okay, Clapeyron, Thorntons, Riddles, and also Watson. Okay, this one. Clapeyron is going to be standalone, but it's quite how to say. It's need the delta H and delta. I still don't remember this one. Okay, if I remember, but it's quite delta V and dp. There's a derivation, or we have to do the integration. dp saturated divided by dt. But Riddle is the easiest equations. Okay. Okay, this one Riddle. Okay. Riddle equation is we have to calculate rate of vibration at the normal boiling point. Riddle this one. But generally we will combine this one to. Watson is like a correlation. If you still remember, or in chapter 3, right, we do correlations between initial condition and final condition. It's same like a Watson equation. For this Watson is the correlation between initial and final. Okay, but we do use the information from the Riddle equation. Okay, Riedel equation also can be standalone, but we calculate at the normal boiling point. But Watson need the information from the Riedel. Sometimes we need it because sometimes for the initial condition we cannot get the information, so we have to calculate by using Riedel equation. Thornton's rules is like approximations. Okay, not really accurate. It's like approximate value lah. Okay. For example, like argon, nitrogen, what is the approximate value for the heat of the evaporation Thornton's rule. But generally we use Clapeyron, Riedel, and also Watson. Okay. So if we do the energy balance, if you still remember, for the two-phase system, the degree of freedom is only 1. Okay. So we have to specify one thermodynamic properties. Okay. And another thermodynamic properties we can vary. Okay. So for example, this one delta H is a vibration at the normal boiling point. Boiling point is a starting of for the two-phase system. Okay. Okay. So for the Clapeyron equations, okay, if you look at here that coexistence of two phases, all right. So I told you latent heat accompanying a phase change is a function of temperature related to Clapeyron equation. So change in the enthalpy latent heat, this one enthalpy for the latent heat. There's a change in the volumes, so meaning that there's a volume for the liquid and also the vapor. Okay, this one vapor pressure. Okay, so that's why it's quite hard to say. There's a dp saturated and divided by dt. So we have to know how to calculate this one. Okay. So to determine the delta V, okay, from this equation, you need the volume at liquid and also volume in the vapor, right? Okay. So for the liquid, you can use a Racket equation. That one is for the liquid. Okay. So and dp divided by dt. Okay, this one, right? How can we get this equation? How can we get this information? This one is from the endpoint. Okay, endpoint equation. Okay. So if we apply to the evaporation of the pure liquid, right? This one's latent heat of vaporization, slope of the vapor pressure, difference between molar volume of saturated liquid and also saturated vapor. This is what I already tell you. Okay, because for the vapor, right, for the liquid PV, right? So this one is a range for the liquid. This one is for the vapor. So there is a difference here. Okay. Slope or we use an Antoine equation. Okay. For example, this one is for the water 150 degrees C. You can use the Clapeyron equations, okay, to calculate the what is it? The enthalpy or the volumes as well as temperature. Okay. I think this one is for delta H vapor. But we have another method by using a steam table. Okay. That one is steam table. Yeah. You have to use a steam table. I think it's in appendix. There is an appendix. I don't remember which appendix. Superheated steam table F. Okay, appendix F. That one is for the saturated steam. But that one is only for the water steam. For the other component we cannot calculate. Okay. Any questions about this one? About the Clapeyron equations? Okay, let's see the example. If you look at here, right? I think it's quite long. This one I will explain in the next class. The tutorial. Okay, wait. I just explain the okay. I just explain the equation first. Okay. After Clapeyron, this one next class, okay, I will explain during the 1 hour class. Please remind me next week. For the approximation method, we have two. Okay. First is prediction from the normal boiling point. This is Thornton's laws, and another one is Riedel equation. But another one is estimation of the heat evaporations. T from the known value of the single T, meaning that initial you know or final you know. So we do the correlation by using a Watson equation. Okay. So this is a Thornton's law. Look at here that latent heat evaporations pure liquid at the normal boiling point. For example, like argon, right? But this one is just a how to say not really accurate. We call it, that's why we call it approximation. Okay. But I don't think so. I would like to suggest this one. For me, you can use Riedel equation. So the accuracy is about of 5%. Okay. This is from the normal boiling point because the information we can get the temperature at the normal boiling because this is starting of the for the two-phase system, right? Okay. So this one is reduced temperature at the normal boiling point, meaning that Tn divided by Tc. Okay, PC critical pressure you can get from the table. Okay. Appendix B. Okay. So there's a critical pressure, and then you can calculate delta H. Okay. So for example, for the water, right? Okay. Tn is, this is 100 degrees C, right? Okay. PC is 220. This one. This is critical pressure. Of course, it's 220. Then TRN just divide 1 minus with 1.013, so you can get 23228. So you can compare with the steam table. It's almost similar. Okay, this one 2328. Okay, and then for the Watson, okay, Watson equation, it's stated that any temperature from the known value at the single T, meaning that at initial value. Okay, so we know that maybe T1 or T2. Okay, just do the how to say the correlation so we can calculate the delta H evaporation at final temperature. This one we can calculate by using Riedel. Okay, we could combine Riedel and Watson to solve delta H vaporization. And so this one is from the information is given. Okay, this one is from the Riedel. Or for example, delta H is from the Riedel. Okay, we calculate delta H vapor. Okay, so meaning that is a combination of Watson and also Riedel is you can determine the final enthalpy at the final condition. Okay, any questions about the approximation method before we stop? This one I will discuss next week. Example 5, 6, and tutorial 3. Okay, if you have time, please do this one first if you know, but it's okay if you don't do. Please understand first the equation. Okay, this one you will use it in chapter 6 also. Okay. Okay, any question before we stop? Because I have to. We already
Doctor,
covered session. Yes.
sorry, I have a question about the previous topic
What
about
topic?
the heat capacity.
Uh-huh.
For the do you mind if I share the screen?
What is it?
We are in page slide 10.
Slide 10. Okay.
Yeah. Different from mine.
This one.
Why different from mine?
Which one?
Yeah.
What's the
16, sorry. 16, sorry.
Okay.
Just the equation only lah.
Mm-hmm.
So if we can't use the equation because it's ideal case 1. So we need to use the equation stated by Dr. just now called the top A, that one, right?
Yeah,
If
this
we
one.
use this, it's wrong, right?
Yeah, this one is only for ideal gas state.
Even though get same answer also wrong lah.
Because I think there is a range of the temperature if when you considering the ideal gas. I think it's new book they have the range. Ada tak dalam tu? New book. Range of the temperature when you want to use this direct.
If I So see the textbook, textbook, it state from 298K to T max.
It's possible to directly you use this one. There's a range of the temperature.
But
But
we just use
more than that, you
use-
have to use this one. Okay. I think
we just use this one.
the one that stated is there's a range because old book they don't state the temperature. As I told you, this one is for the wide range of the temperature, like a 500 or something.
Alright,
But for me, I would like to suggest if high temperature 100, you just use this one rather than use this one, right? Because this is only for the ideal gas.
alright, understood. Thank you.
Maybe if temperature 87 100 is acceptable because it's not stated about the pressure, right? But it's combining with the pressure also. I don't think you can use directly this equation. Just use this one. Okay. Okay.
Okay, thank you.
Okay. Anything before we stop? Okay, so if you have no questions, that's all for today. Okay. We will continue